In this lesson, we will explore another application of calculus to physics called moments, centers of mass, and centroids. So the big question we're trying to address in this lesson is this: suppose we have some kind of weird shaped plate, and this plate has uniform density. The question is how would we find some point P such that when we take the plate and try to balance it on something like our finger or a fulcrum, that this plate will balance perfectly. That is called the centroid of the region. So to figure that out, let's start with a simple one-dimensional discrete case. So consider we have a rod with two masses. You could think kids. We call them M1 and M2, and they're attached to this rod with negligible mass at a distance. So M1 is a distance of D1 from the fulcrum, and M2 is a distance of D2 from the fulcrum. And in order for this thing to balance, what has to happen is that M1 times D1 has to equal M2 times D2. That is called the law of the lever, and was discovered by Archimedes. So the mass of the object at this end times its distance from the fulcrum must equal the mass of the object at that end times its distance to the fulcrum. Now, next, suppose the rod is instead on the x-axis. So we have some point x1, which has a mass of m1. We have some point x2 that has a mass of m2 located there, and that fulcrum point, we're going to call that x bar. Now this distance here is x bar minus x1. This distance here is x2 minus x bar. Using the law of the lever, we have that this red distance times mass 1, so m1 times x bar minus x1 must equal m2 times x2 minus x bar. So x bar is the location of that center of mass, so let's solve for it. So distribute my m1 and m2. I have m1 x bar minus m1 x1 equals m2 x2 minus m2 x bar. So I'm going to move this to the other side, giving me m1 x bar plus m2 x bar equals m1 x1 plus m2 x2. So I moved this over there. Now factor out that x bar times m1 plus m2 is equal to m1 x1 plus m2 x2, or x bar is equal to m1 x1 plus m2 x2 over m1 plus m2. Now, in the numerator, generally speaking, mi times xi, that is called a moment. So in the numerator we have the sum of the moments divided by the total mass. A similar argument we'll get if you have 3 points or 4 points, you're trying to balance them, you're going to have the sum of the moments divided by the sum of the mass, and that will give you the location that is the center of mass for that system. So suppose we have a 20-pound child and a 60-pound child that sit on a seesaw that is 5 feet long. So here's our 5-foot seesaw. So the 20-pound kid is over here, and the 60-pound kid is over there. Call the distance from the 20-pound kid to the fulcrum. Call that x. He's going to balance, actually, that'd be way over there. So if this distance is x, this distance here is 5 minus x. And we can use the law of the lever to figure out where this x actually is. So we have 20 times x must equal 60 times 5 minus x for that seesaw to be balanced. That gives us 20x equals 300 minus 60x. 80x is equal to 300, and x is equal to 30 over 8, or 15 quarters, or 3.75. So we should locate the fulcrum 3.75 feet from the 20-pound child. Next, suppose we have a system of point masses. So mass 1, the mass of the first point is 7, the mass of the second point is 3, and the mass of the third point is 5. And these points are lying on the x-axis at the points -5, 1, and 3. So let's just draw a little picture. So at -5 we have x1, it has a mass of 7. At 1 we have a mass of 3, and at 3 we have a mass of 5. Now x bar will be given by the sum of the moments, so m1 x1 plus m2 x2 plus m3 x3 divided by the total mass, so m1 plus m2 plus m3. So that's 7 times -5 plus 3 times 1 plus 5 times 3 divided by 3 plus 7 plus 5, which gives us x bar equal to -17 over 15. So next, suppose we have a system of n particles with masses m1, m2, up through mn, located at points in the two-dimensional plane. So let's just draw a picture of 3 of those masses. Suppose we have the following. We have m1 over here at a distance of x1 and a height of y1. m2 is down here at a distance of x2 and some y2. And m3 is over here, distance x3, height y3. So the first thing that we're going to do is find the moment about the y-axis. So moment about the y-axis. So the idea is this. So we'll attack the problem in the following manner. First, we're going to balance the system this way about the y-axis. Think about fixing a plane parallel to the y-axis, your hand or something like that, and trying to balance the system that way. That's called the moment about the y-axis. Then, after we find that, we balance the system this way. That's called the moment about the x-axis. And once we have an x-coordinate and the y-coordinate, those two coordinates give us the center of mass. So to find the moment about the y-axis, we use an argument similar to the previous one. The sum of the moments will be the sum from I equals 1 to n of mixi. What that means is we're going to take m1x1 plus m2x2 all the way up to mnxn. And the moment about the x-axis will be given by mx, which is equal to a sum from I equals 1 to n of mi times the y-coordinates. So that's m1, y1 up to mn, yn. Next, we let lowercase m be equal to the total mass, which is m1 plus m2 up to mn. And then the location of the center of mass, x bar, is given by the sum of the moments, so that will be these, so my divided by the total mass. And y bar, similarly, is given by the sum of the moments mx over m. So let's apply that to this system. So first, we know that x bar is equal to my over m, and y bar is equal to mx over m. Now to find my, that will be equal to m1x1 plus m2x2 plus m3x3 plus m4x4. So the mass of the first point is 12, has an x-coordinate of 2, plus 6 times -1, plus 4.5 times 6, plus 15 times 2, which equals 75. And mx is equal to m1y1 plus m2y2 plus m3y3 plus m4y4, which is found by computing 12 times 3 plus 6 times 5 plus 4.5 times 8 plus 15 times -2. And that all adds up to 72. Now to find x bar and y bar, we have to also find the total mass lowercase m, and that is 12 plus 6 plus 4.5 plus 15, or 37.5. Now we know that x bar is given as 75 divided by 37.5, which is 2, and y bar is given by 72 over 37.5, which can be written as 144 over 75. So the center of mass is 2, 144 over 75. Now, suppose we have a region R of uniform density ρ that lies between two curves y equals f of x and y equals g of x, where f of x is greater than g of x. So here we have f of x, here we have some g of x, and we want to find the center of mass of that object between A and B. Now the first thing we will do is find the moments. Now the moment about the x-axis is given by this formula, and the moment about the y-axis is given by this formula. And the center of mass is given by x bar equals my over m, and y bar equals mx over m. The first thing we are going to do is find the total mass of this region. Now, assuming we have density ρ, the total mass lowercase m is equal to density times the area of the region. So in this case that is ρ, and you learn to find the area of this region by taking an integral from a to b, f of x minus g of x dx, or letting this expression equal a, the mass is ρ times the area. Next, let's discuss where this formula, which is my, comes from. So you would like to approximate the moments about the y-axis. So we divide a, b up into little intervals, take a subinterval, and we'll say that that has width delta x, and we're going to let x sub I equal the center of the ith rectangle. Alright, then the mass of that rectangle, let's call that lowercase m sub I, is equal to rho, so that's the density, times its area, which is f of x sub I minus g of x sub I times delta x. And just because you're approximating this by a rectangle, that's the height times the base. We then have that the moments about the y-axis are about equal to a sum of all these individual m sub i's. So from I equals 1 to n, m sub I, x sub I, or a sum from I equals 1 to n of rho times f of x sub I minus g of x sub I, x sub I delta x. Now to find my exactly, we'll take a limit as n goes to infinity of this expression, and as it has in every other lesson in this chapter, that is going to become an integral from a to b of rho times f of x minus g of x times x dx. So we have that my, the moments about the y-axis, is equal to, factor out that rho, it's a constant, the integral from a to b, x times f of x minus g of x dx. And that was given to you in the last slide. And then that tells us that x bar is equal to my over lowercase m. When you do that division, the rows will cancel, and we will have 1 over a times the integral from a to b, x, f of x minus g of x dx. The last thing we need to do is show why the formula for y bar is given by this expression here. So just like figuring out m sub y, when we find m sub x, this will be approximated by a sum from I equals 1 to n of m sub I times y sub I. Now, the mass of that box has not changed, so m sub I is still equal to rho times f of x sub I minus g of x sub I times delta x. What we need to figure out is what y sub I is. So in this little box, we're finding the center y value. It's going to be in the middle because the thing has uniform density. So y sub I will be the average of the y values. That is f of x sub I, so the average of this y value plus that y value divided by 2. And that gives us that m sub x is about equal to a sum from I equals 1 to n rho times f of x sub I minus g of x sub I multiplied by f of x sub I plus g of x sub I over 2, delta x there on the end. And to find mx, we take a limit as n goes to infinity, and that gives us the integral from a to b. Now I'm going to factor that rho out, and I'll have 1/2, and this is f of x minus g of x multiplied by f of x plus g of x dx. And you can leave that in factored form, or if you multiply those together, we have the integral from a to b 1/2 f of x, the quantity squared, minus g of x, the quantity squared, dx. When we find y bar, we take the expression for mx and divide it by the total mass. And in that case, the rows will cancel, and we will have 1 over a times the integral from a to b, 1/2 f of x, quantity squared, minus g of x, quantity squared, dx. Looks like I need a 1/2 there. So let's use those formulas to find the center of mass of a lamina of uniform density. So we are going to find the moment about the x-axis, the moment about the y-axis, and x bar, y bar for the lamina of uniform density, rho, bounded by the graphs of the equations y equals 9 minus x squared and y equals 0. So first let's graph y equals 9 minus x squared. It's a parabola, shifted up 9, it's upside down. This intersects the x-axis at plus or minus 3. So this is the region that we're looking at. Now, the first thing that we will do is find the moment about the x-axis. Now that is given by the formula rho times the integral from a to b of 1/2 f of x squared minus g of x squared dx. Now that's rho over 2. Now in this case, my integral is from -3 to 3, and my f of x function is 9 minus x squared. My g of x function, this lower curve, is just y equals 0, so minus 0 squared dx. Now because we have an even function, we can use some symmetry to give us a little bit of a shortcut here. I can make this into rho over 2 times twice the integral from 0 to 3 of 9 minus x squared. I'm also going to square that quantity, which gives me 81 minus 18x squared plus x to the 4th dx. Or rho times 81x minus 6x cubed plus 1/5 x to the 5th, evaluated from 0 to 3. And when you work that all out, you end up with 648 over 5 rho. Next, we'll find the moment about the y-axis. Now remember, the moment about the y-axis means you sort of fix a vertical line. You're looking for, if you have your hand underneath this object going vertically, where would it balance? And I think it's pretty obvious that it's probably going to balance in the middle because of the symmetry of this curve. Now that is going to be true. Let's just verify it by using that formula, and if you notice this elsewhere, you can use it on your homework without doing any work. So the formula for the moment about the y-axis is rho times the integral from a to b, x times f of x minus g of x dx. Or that is rho times the integral from -3 to 3 of x times 9 minus x squared dx. Or rho times the integral from -3 to 3 of 9x minus x cubed dx. Now you can do one of two things. You could notice that this is an odd function, and you have a symmetric integral, therefore this is equal to 0. But if you forget that and you just anti-differentiate and keep going, you end up with 9 over 2x squared minus 1/4 x to the 4th. And that gives you rho times 81 over 2 minus 81 over 4, that's plugging in 3, minus 81 over 2, minus 81 over 4. So you plug in negative 3, and you can see that those two terms will cancel, these two terms will cancel. We have rho times 0, which is going to give us 0. The last thing we have to do is find x bar and y bar. Now remember that x bar is given by the moment about the y-axis divided by the total mass, and y bar is given by the moment about the x-axis divided by the total mass. So what we do not know yet is this total mass. So the total mass is equal to rho times the integral from a to b of f of x minus g of x dx. So we have rho times the integral from negative 3 to 3 of 9 minus x squared minus 0 dx. So this 9 minus x squared is an even function, so we can compute 2 rho, the integral from 0 to 3, 9 minus x squared dx. Now that gives us 2 rho times 9x minus x cubed over 3. So that will be 2 rho times 27 minus 27 thirds, which is 9. So 27 minus 9 is 18 times 2 is 36 rho. Alright, thus x bar is equal to my over m. Now x bar was, my was 0, so x bar is 0 over 36 rho, so thus x bar is equal to 0. So the x-coordinate of your center of mass is 0, which makes sense if you look at the picture. Now y bar, that will equal mx divided by lowercase m. So mx is 648 rho over 5 multiplied by 1 over 36 rho. And that gives, once you reduce, 18 over 5, or 3.6. So your center of mass, x bar, y bar, is 0, 3.6. And that should sort of make sense from your picture. If you take a look at this, that center of mass is a little bit lower down there, which, since this area is more, that's kind of looks like where it should be. So let's do another one. Find mx, my, and x bar, y bar for the lamina of uniform density rho bounded by the graphs of the equations negative x squared plus 4x plus 2 and y equals x plus 2. So first, let's graph these equations. So negative x squared plus 4x plus 2 is a parabola. It will be helpful probably to find the vertex using the formula negative b over 2a. So that will be negative 4 over 2 times negative 1. So that is 2. So the x-coordinate of the vertex is 2. And the y-coordinate, plug in 2. We have negative 4 plus 8 plus 2. The y-coordinate is 6. So over 2 up 6. And then just input some values for x. If you input 0, we get out 2. And you can reflect that over there. And if we input 1, we get out 5. So roughly speaking, there is that parabola. Now x plus 2 begins at 2 and has slope 1, so rise 1, run 1. And there's our region. The intersection points are at x equals 0 and x equals 3, which you can verify by setting the curves equal to one another and solving if you would like. Now first, let's find mx. So mx is equal to rho times the integral from a to b of 1/2 f of x quantity squared minus g of x quantity squared dx. So in this case we have rho times the integral from 0 to 3. Let's just say rho over 2. The f of x is my upper curve, which is negative x squared plus 4x plus 2 quantity squared minus x plus 2 squared dx. Now when everything expands and you combine like terms, we end up with the integral from 0 to 3 of x to the 4th minus 8x cubed plus 12x squared plus 16x plus 4, that's the first thing expanded, minus x squared plus 4x plus 4. And the rest is just pretty tedious, but when you anti-differentiate and evaluate this at 0 and 3, we end up with rho over 2 times 198 over 5, which gives us that mx is equal to 99 rho over 5. The most important part here is setting this up. The rest of it is just quite tedious. So there's mx. Next we find my. So my is equal to rho times the integral from a to b of x times f of x minus g of x. So in our particular case, we have rho times the integral from 0 to 3. F of x is negative, so of x times negative x squared plus 4x plus 2 minus the quantity x plus 2 dx, which simplifies to rho times the integral from 0 to 3 of negative x cubed plus 3x squared dx. Now we anti-differentiate and we end up with rho times negative 1/4 x to the 4th plus x cubed, evaluated from 0 to 3. And that ends up as 27 rho over 4. Next, let's find x bar and y bar. So x bar is given by my divided by the total mass m, and y bar is given by mx divided by the total mass m. So m is equal to rho times the integral from a to b of f of x minus g of x dx. For our particular case, we have rho times the integral from 0 to 3, negative x squared plus 4x plus 2 minus the quantity x plus 2 dx, or rho times the integral from 0 to 3, negative x squared plus 3x dx. That is rho times negative x cubed over 3 plus 3x squared over 2, evaluated from 0 to 3, which works out to be 9/2 rho. Now, using that, we have that x bar is equal to my over m, and we had that my was 27 rho over 4. Dividing by m is the same as multiplying by the reciprocal, so we'll have 2 over 9 rho. And that ends up, we end up with x bar is equal to 3 over 2. Y bar is given by mx, which was 99 rho over 5, multiplied by 2 over 9 rho, and thus y bar is 22 over 5. Centroids can also be used to find areas of a plane region. So this is the Theorem of Papas. It says that if you have R as a plane region that lies entirely on one side of a line L in a plane, and if R is rotated about L, then the volume of the side of the resulting solid is the area of R multiplied by the distance traveled by the centroid of R. So suppose we will prove this in the case that the line of rotation is the y-axis, and we have two curves f of x and g of x. And we want to rotate the region between A and B about the y-axis. And to prove this, you use cylindrical shells. The volume is equal to the integral from A to B. Think circumference, so 2 pi x, times height, which is f of x minus g of x, thickness, which is dx. So that is equal to 2 pi times the integral from A to B, x multiplied by f of x minus g of x dx. Now remember, x bar is equal to 1 over a times the integral from a to b of x times f of x minus g of x dx. And do you see that this is that expression? So solving for that expression, we have a times x bar is equal to the integral from a to b of x multiplied by f of x minus g of x dx. So the formula over here is really 2 pi x bar times a, and 2 pi x bar, that is the distance traveled by the centroid. So say here is the centroid. It goes around the y-axis, how far it travels in a circle, and the distance it travels is the circumference of that circle, which is 2 pi r, and r is x bar. So let's use that to find the volumes of some solids. So we are going to find the volume of the solid of revolution obtained when the circle y equals x minus 5 squared plus y squared equals 16 is rotated about the y-axis. So this is a circle of radius 4 centered at 5, 0. So 1, 2, 3, 4, 5. 1, 2, 3, 4. So 4 up. So there's the center. 4 back. 4 high. 4 down. And here is what we're rotating around the y-axis. Now think for a second, what kind of shape is that going to yield? So this spins around, comes back on itself, it makes a donut shape called a torus. So we'll find the volume using the formula 2 pi x bar times a. So first of all, you have a circle. You are allowed to use the fact that the area of a circle is pi r squared. In this case, this circle has radius 4, so we have pi times 4 squared, or 16 pi. Now, due to symmetry, x bar is the center of this circle. So there is x bar is 5. So the volume of this torus is 2 pi times 5 times 16 pi, or 160 pi squared. In the next example, we will use the theorem of Papas to find the volume of the solid formed by revolving the region bounded by y equals x, y equals 4, and x equals 0 about the x-axis. So there's y equals x, here's y equals 4. We're going to rotate this triangle about the x-axis. Now in this case, the distance traveled by the centroid is given by 2 pi y bar. So we'll find the volume by finding 2 pi y bar times a. Now first of all, this is a triangle, so the area is 1/2 the base times the height. So 1/2 times 4 times 4, which is 8. y bar is given by the 1 over a times the integral from a to b of 1/2 f of x squared minus g of x squared dx. So y bar is 1 over 8 times the integral from 0 to 4, 1/2. My upper curve f of x is the constant curve 4, so times 4 squared minus my lower curve is x, so x squared dx. That gives us 1/16 times 4x minus x cubed over 3, evaluated from 0 to 4, which is 1/16 times 128 over 3, or 8/3. Now when we apply the theorem of Papas, we have that the volume is 2 pi y bar times a, so that will be 2 pi times 8/3 times 8, or 128 pi over 3. And if you don't believe this, or you need to check your answer, you could use some other method, such as cylindrical shells or disks, to find the volume of this solid of revolution, and you will get this exact same volume we got here.